No one pick me up?
No.
Come on, Levi.
That would be like 15 minutes.
I'm just kidding. I wasn't expecting you to. Are you still planning to meet?
Yeah.
Lad? I'm getting the impression I'm riding with you now.
Yeah. Because I think Whitney emailed us saying that she's riding with Brandon, not this Brandon, but the other Brandon, and Braden.
Yeah, I saw the
Right.
Brandon in my email list. In email list, Brandon's name is there.
Yeah, I got confused and I added him too.
Are you still, is everyone else
So
close to
this-
campus, or?
He's UV. Where are you, Aaron?
H3, so like right next to the hospital.
On like Broadway? Oh, the bus don't run.
Today's Valentine's Day?
See?
Oh, yeah, I wore red on purpose too then.
That's my room.
It's got red. Close enough.
Is your undershirt red?
Yes.
Oh,
I did wear red.
so we have the lame.
No, I got red. It's there.
Can we start?
Yeah.
Thank you. So we are in the quantum chemistry 2 class. We are having your free view presentations, which will count as midterm.
Midterm. Oh boy.
And the last time we met, we finished background for the perturbation theory, first and order, second order corrections, energy first order for wave function, and now we are going through applications of the perturbation theory. So let's try to spend like 4 minutes plus 2 minutes questions, if possible. All your materials are uploaded to this PC and numbered in the order that it is here, and also labeled according to your names. So you come to the computer, find your presentation, and just bring it up to share. So the very simplified summary of our last meeting is that small perturbation in frequent practical applications introduce splitting of the levels and lifts the degeneracy. But nature of this external perturbation can be different. So let me announce the first presenter, Deyan Mikhaylov, who will tell a story how the perturbation theory applies to quantum chemistry and gives rise to a correction to the Hartree-Fock theory named as MP2 perturbation theory.
Oh, yeah.
So
Oh my
click
God.
here, stand there.
Oh, there's a timer on here. Click here. Okay. Okay, so we are all students here. I don't. This is my interpretation of Moller-Plesset theory, as far as I could go into it. So it might be wrong, but this is how I understand it. It's very complicated, by the way. So right off the bat, I wanna start by saying that Moller-Plesset perturbation theory is perturbation theory in the basis of Hartree-Fock orbitals. So let's review Hartree-Fock equations and define 1 and 2 electron operators. We have a kinetic term acting on some orbital plus ion electron interaction term acting on some orbital So these are operators, right? Operator acting on orbital, operator acting on orbital, returns, eigenvalue, and eigenfunction, right? This is like Schrodinger equation. So these are what we call 1 and 2 electron operators because they only act on one orbital. The electron-electron interaction in Hartree-Fock looks like this, an direct and an exchange term. Direct term depends on the density, right, and acts directly on the eigenfunction that we are looking for, but the exchange term doesn't. For the exchange term, you need to integrate over the orbital that you're looking for. The orbital that you're looking for that appears on the right-hand equation. So this is why this is called non-local, and that's why this is computationally more expensive. So these two terms we're going to define as Hartree-Fock two-body potentials, and these, the first two, as one electron operators. So these potentials are two-body operators. These are one-body operators. Okay, so this brief review of Hartree-Fock. So this is very important to understand, and is kind of the philosophy of the method. So I try to explain it very well in this blue text, but I wrote out on the board somewhat more detailed explanation. So if everyone can turn to the board.
Go to the board.
So we have a total Hamiltonian. This is a Hamiltonian for any system. You have a kinetic term, ion, electron interaction, and electron-electron interaction. So this is a true Hamiltonian. It doesn't know about any approximations or anything. And the non-interacting part of the Hamiltonian is the kinetic term and potential due to ions. So, but if you wanna work in the basis of Hartree-Fock orbitals, once you solve your Hartree-Fock equations and you obtain your Hartree-Fock orbitals, you've already used this extra Hartree-Fock potential that we went over in the first slide, where the direct and exchange term come from. So if you want to do perturbation in the basis of Hartree-Fock orbitals, you have to use this Hamiltonian as your non-interacting Hamiltonian. Right? Although it has this interaction piece, now that you're working in this basis where you have non-interacting molecular orbitals, you have to treat this as part of your non-interacting Hamiltonian. So if you go ahead and plug in your true Hamiltonian and your new Hartree-Fock free Hamiltonian and your perturbation, you can solve for your perturbation, where you have this true electron-electron interaction, but now you gotta subtract the Hartree-Fock potential. So that's everywhere you go to look at perturbation theory, you will see the subtraction of this two-body potential. This is where it comes from. Because you're working in a basis of orbitals, which you're treating as non-interacting, but you obtain them with a self-consistently solved equation that includes interactions. So this is the logic of Moller-Plesset theory. Okay, so your perturbation is this true perturbation that you want to account for, but you have to subtract your Hartree-Fock potential. Okay, so this was complicated Hartree-Fock Moller-Plesset philosophy. So now let's just do Moller-Plesset perturbation. Do zeroth order, you get the same expression you had in class. You take the expectation value of your non-interacting Hamiltonian, where your non-interacting Hamiltonian is only the kinetic and the ion part of your only these parts of your Hartree-Fock. So the Hartree-Fock potential has been kind of absorbed into, well, it's not absorbed into the perturbation, but our free Hamiltonian I cast as this true free Hamiltonian plus this Hartree-Fock. So to zeroth order, we don't know anything about even the Hartree-Fock potential, right? These wave functions are obtained through the Hartree-Fock method, in terms of in terms of Hartree-Fock orbitals, you gotta construct your Slater determinant. But you obtain a sum. This way, you obtain a sum of Hartree-Fock orbitals. The sum of the energies of the Hartree-Fock orbitals. But that's not the true Hartree-Fock ground state density, ground state energy that you get when you run your Hartree-Fock software. What Hartree-Fock software does is it goes to first order correction in Moller-Plesset perturbation theory, where this potential is known because you define this potential. You define it so that you can better account for correlations. The philosophy is probably similar to functionals in density functional theory, where they account for correlations. I wasn't able to find the actual functional form of any of this. But if you dig deep into the literature, I think you'll be able to find it. But it's beyond this talk, right? This is just the philosophy of the method. So taking this simple enough and accounting for correlations and the Hartree-Fock potential, taking this inner product will give you correction to these sum of these energies of the molecular orbitals. And that is the true Hartree-Fock ground state energy. So if you run your Hartree-Fock and you find your just energies of your molecular orbitals and you take this, it's wrong. This is not your ground state density. I think this is built into softwares so that when you ask for the ground state energy, it will give you this, the corrected ground state density. So the philosophy here is a little bit self-inconsistent because your molecular orbitals are obtained through the Hartree-Fock equations. But your ground state energy is not the sum of those molecular orbitals. An additional perturbation is applied where the ground state, where the molecular orbitals are taken into account to calculate for this correction to the sum of those energies. Okay, so here, this is what's done in pretty much every Hartree-Fock software. So you never see MP1, right? When you type in keywords. I don't think so. At least I haven't seen. So because this is inside the Hartree-Fock. But MP2 is an option. And that's where you have to go if you want to further correct for your energies. But now you have to calculate the correction of your Hartree-Fock orbitals. And this is very complicated. The equations would turn out to be exactly like the we derived in class. On just a side note, the way this is done is it's used Slater-Condon rules, where any two-body operator, when acting on a wave function, gives you a sum of all possible, gives you that operator acting on the sum of all possible pairs of orbitals. So it's like making an approximation and saying all interactions occur pairwise, which is, I don't think, it might not even be an approximation. Well, it should be, because three body interactions are also there, but I think they're much smaller contributions to this total inner product. But when you run MP2, this is what you calculate. And now this is much more computationally expensive to calculate this inner product, because you have all these possible pairs of orbitals that you have to calculate with your two-body potential. And this subtracting this piece, which is non-local, makes it adds to the complexity. So this is what you do in MP2. In MP3, you can derive the equations and follow the same Slater-Condon rules, and you get similar stuff. So this is it.
Okay, yeah. Any questions to the speaker? Levi, please.
Why don't we have lambda within your last line?
I don't know. It doesn't need to be there. You're right.
He placed lambda equals 1.
Yeah, lambda is, this is in lambda equals.
But he has it explicitly on the right, the left.
It's
Formally, you are right.
Okay. I just wanted to give them my bearings.
More questions?
it,
To Deyan? Deyan? I do have one.
yeah.
So when you write MP2 calculations to semiconductor quantum dots, do you get larger or smaller compared to Hartree-Fock? Or even if you didn't try it, what do you expect?
It should be smaller, because further it should be smaller because your perturbation accounts for correlations, and correlations lower the gap from non-interacting Hamiltonian.
Okay, let's thank Deyan once again. And the next presenter is Levi Lystrom, who will tell a story about another type of perturbation that molecules surrounding an ion in metal-organic compounds impose on the metal ion and induce splitting. So it is a common knowledge that a lot of chemists use right away, but here are the quantum background of this effect.
Hey, Dimitri. So I'm going to talk about perturbation theory for octahedral splitting and d electrons. So first, what we assume with perturbation theory is we've already solved the Schrodinger equation, but d orbitals are degenerate, and this is a problem. So what we want to do is only solve the portion for the d orbitals and leave everything else the same, because realistically the lower orbitals and higher orbitals only affect higher excitations, not towards the band gap. So what we do is we say we have an ion, and then we have 6 points where ligands can come in and bind, and this satisfies a second order differential equation. So we can use the eigenvalues of the solid harmonics for exact solutions, and we just do all sorts of linear combinations. And it turns out that we can only use certain M and L's, which I'm not going to get into because the sources where I read them, they didn't really explain it that well. But we can only have even L's, so 1, 2, 4, 6, 8, and so forth. 2 are they're not symmetric, so we exclude 2, so we go to 4, and 4 is good enough for d orbitals, so they just stick with.
To go forward, the
red sphere and black spheres, which are of which charge?
So the red is positive and the black are either negative or they induce a dipole.
Okay, so it is electrostatic
Yes.
effect of black points onto red point.
Yes, which causes the splitting.
Okay,
So when we get the d orbital and we take out the energy and we make this matrix, we get a whole bunch of different commutations. So like d negative 2, so this is the ml term. So this is the same, and then we just do it like we did in class.
so what the index -1, -2 mean?
That's ml. So
Well, the quantum number of what?
angular momentum.
Projection?
Yeah.
Okay.
Yeah. So this is what we want to solve, and way back in like 1920, they didn't have computers, so they couldn't just take this, plug everything in, and have the computer diagonalize it. So what they wanted to do was use different linear combinations that make it much easier. So what you typically see is like T2G and EG, which are the symmetry operators for the two energy splits. And there are two types to get EG, where what is dx2 minus dx squared minus y squared, which is the linear combination of the second and negative with the coefficient, and then dz squared, if you remember from the last talk, is the only d orbital that is plotted that is not a linear combination. It is just the ml equals 0. And then it's the same for T2G. And these are the relationships. So when they plug everything into the Hamiltonian, they go from this to a diagonal matrix, which is much better to solve. And all we need to do is the x terms and the y terms. So what you can do is take the trace of the original matrix and the diagonal matrix, and the trace should be the same. So then we get 5a plus 3x plus 2y is equal to 5a. So therefore 3x plus 2y should equal 0. So what you can do is send it equality, and you get that x is negative for dq, and then y is 6dq.
So what is D and what is Q? What does this notation stand for?
So d is if you solved the linear combination of the orbitals, there's a minus d and then the basics function, and d is that, and q is how much the ligand field strength is, or something like that. So this dq term pretty much tells you how strong the ligand field is. So if your ligand field is very strong, then it will split more. Your dq will be larger. So this is the energy splitting that we get. So this is 10 dq. So then this is -4 and positive 6 dq. And then we get our E set, which is our 2 and then T2G set. Any questions?
Let's thank Levi first for volunteering for this complicated subject. And are there any questions to the speaker?
Dang it, I wanted to
well,
use this because I knew that I was going to get a hard question. So, like, from Millionaire, when they ask a difficult question, the moment that you know you're not going to be a millionaire.
So, can you intuitively explain this splitting? Just in figures. Why some orbitals go higher up in energy and some orbitals
drop down?
So
Why the 6 negative ligands affect this symmetrized orbitals in a different way?
if the lobes of the orbitals correspond to the points of the ligands, that could either decrease energy or increase energy.
Excellent. More questions? If no, yes?
I was gonna ask. No, I can look this up myself. It's just slow things. I was
Okay.
gonna ask about the solid harmonics. Like, what do they look like? Functional.
I think those are like hydrogen, like orbitals.
No, what is the solution to this Poisson equation when there is no charge, right?
I didn't look into that.
So there.
It is spherically symmetrical.
Yeah. Yeah. Well, it's spherical symmetry. What's the function? It's a bunch of sines and cosines.
No, it's more like spherical harmonics. You can expand the field of electrostatic field of point charges in terms of spherical harmonics.
And spherical harmonics. What do they look like?
Same as for hydrogen atom.
Oh, so E to negative.
Yes. If there are no more questions,
Can you go to your second to last slide? So, one more forward. So how come adding the ligands results in an increased energy from the free metal ion?
So free metal, and then this is within like a magnetic field. So this is just increasing the potential, and then from this point they split.
Okay. So, because wouldn't you expect your total energy to go down if you put the free metal ion and the ligands together? But I guess maybe, but okay, I see. You're doing free metal ion and not free metal ion and ligands.
Yeah. So this is just if you take the metal ion in vacuum, the energy is lower, and then if you put it in potential, then it increases, and then it splits. Right.
very good. Let's thank Levi once again. And the next presenter is Aaron Forde, who will bring us from electrostatics to effect of magnetic fields and spins. With an intention also to depart from isolated atom, maybe hydrogen atom, and see how external fields or maybe fields created inside the same atom can perturb and induce energy level splitting. The floor is yours.
Thank you. So I'm Aaron Forde. I'm going to talk about how relativistic effects in spin orbit terms will result in a breaking degeneracy of the hydrogen atom. So if we just consider, like for the hydrogen atom, just a Coulombic interaction, we get that the energy of the atom just depends on the principal quantum number n. So you wouldn't expect to see any, you would only expect to see singlet spectra and no doublets, no triplets or anything like that. But if you look really closely and pay attention really close, as you see in the top figure on the left, they actually do observe some fine structure splitting of the hydrogen spectra. Where, so to account for this, people propose that perhaps there are relativistic corrections because the electron's going really fast around the proton, and then spin orbit coupling terms as well to account for this. So for relativistic corrections, classically we assume the kinetic energy operator is just p squared over 2m. But then if you account for relativistic corrections, you get a factor in the denominator which accounts for the Lorentz transformations. So we go from classical to relativistic, and then if we want to make it into operator, we have to write it in terms of momentum because we know how to write momentums and operators. So we go p squared c squared plus m squared c to the fourth minus mc squared. And then to just get one factor out of there, we can you can factor out the mc squared out of the radical and then do the fancy powers series expansion, assuming that the momentum is really small. So this is the expansion, and then you can truncate it at the first term, and that'll give us our first order Hamiltonian perturbation correction, as shown in the box. And then for first order energy shift, we can use degenerate energy perturbation theory, where we just stick our perturbation potential in between the known wave functions. And if we do that, the first step is just sticking it in, and then you use these two facts. You can go through all the details. But we end up with the final result of this for the perturbation of the relativistic effects, where it's proportional to the original hydrogen atom energies with some extra factors of principal n, and then quantum number L, which shows up. So the L accounts for the degeneracy, the breaking the degeneracy for going up into that's why you get a doublet for the first excitation for absorption spectra or emission spectra of hydrogen when it comes down. And then the second interaction is a spin-orbit coupling. So if you consider the electron going around the proton, we know that circulating charges, that they produce a magnetic field, as shown in the image over here. So if you get the electron circling, you get a magnetic field pointing up, perpendicular from the plane of circulation. So then that produces a magnetic field. Then if you assume that the electron is like a ball of charge and it's spinning, we can assume that the electron produces a magnetic field by itself, which gives it a magnetic dipole, which is this UE term here. And then the S is the spin of the electron. So we assume that the dipole of the electron interacts with the magnetic field of its circulating, so its spin orbit and its intrinsic spin orbit. We consider those interacting. If we take the dot product of those will give us energies of the dipole in the magnetic field. So we can consider a Hamiltonian if we multiply these together. This would be our Hamiltonian, the dot product of the spin and the angular momentum. And then we can do some fancy mathematics to solve for S and L. If we take the coupling, spin orbit coupling, where we add the angular momentum and then the intrinsic spin together. So we could square it, distribute it, and then we get a factor of 2ls over here. We solve for the 2l dot s. And then each of these magnitudes, they are eigenfunctions. They are, when they operate on the wave function, you get eigenvalues. So J acting on the eigenfunctions, they'll just give us our quantum numbers J, L, and S. And then for the spin orbit term, we also have a factor of 1 over r cubed, and then in the sources I give, they just give out that the expectation value of this is this term here. So if we combine all these facts together and multiply everything out, we get that the eigenvalue, or the energy due to the spin orbit interaction, is this term down here. So then, if we add all these corrections together, so the energy of the hydrogen atom plus the relativistic correction plus the spin orbit correction, we can get the fine structure interactions. So if we add them all together, we get this term here, once you simplify everything together, which is the relativistic and spin orbit corrected hydrogen atom energies. And then the thing to notice is that it depends on quantum number n, and then quantum number j, which is this basically L, because with S is always going to be 1/2 or -1/2. And so this is just an example showing that that you go from different states, that these corrections give different splittings of energy level. So here's the doublet state, and then the triplet, and then so on for different excitations. And then for hydrogen-like atoms, for the spin orbit couplings, we can see that with principal number n, that's the energy of the splitting energy grows with increasing n. And these are just all first column elements. So in summary, the fine structure breaks degeneracy with L. principal quantum number, and then the energies are determined by n and j. And then, so our good quantum numbers NL, SJ, M, and then our bad quantum numbers are the projections MJ and ML. Because since we know the magnitudes of the vectors, we can't know the projections. So that's why MJ and ML are bad quantum numbers in these systems.
Okay, let's thank Aaron for an intense presentation, and questions are very welcome. Yeah?
Can you go back to like 3 slides? One.
Yeah, I skipped over a lot of the math steps because I just wanted to highlight important. So the most left term is just the hydrogen atom. The middle term is the relativistic correction. And then the very right is the spin orbit interaction.
Yeah, yeah. Well, I see alpha squared, which will give you fundamental charge to the fourth divided by h bar squared. But there you have an h bar squared on top, so there is h bar to the fourth. I'm not seeing. I'm wondering how this fine structure constant squared came out.
Probably a lot of factoring. You just try to simplify these terms. Like I didn't work through it all by myself because I didn't have a lot of time. But.
So in spin orbit denominator, you do have symbol A. What does it stand for?
Bohr radius.
How does Bohr radius expressed in fundamental constants? Make sense?
Yeah, yeah. So you have an h bar cubed in the bottom. So, but that's still a factor of h bar above. Anyways, that might answer my question.
Okay. More questions to Aaron? If no, let's thank him once again. So in the story by Aaron, the splitting of levels was introduced by intrinsic magnetic field. And the next presenter, Mohammed Abu Jabed, will tell the story about possibility of level splitting induced by external magnetic field. Okay, floor is yours.
Thank you. So I'm Mohammed. I'm talking about the perturbation due to the external magnetic field known as the Zeeman effect. So in the first one, I'm just trying to define what is the Zeeman effect, and it's named after the Dutch physicist Peter Zeeman, and it's showing. I'm trying to put an example. Of the magnetic. Doesn't work in this computer.
Should have embedded it.
Okay, it's showing that it's actually explaining the sunspot due to the magnetic dipole creation on the sun surfaces. It's giving and initially you see only one spectra here, but after the increase the dipole moments and with the spin position, it's split it in the 3 different spectra. It's a very I like that video, but I don't know why it's playing here. So this is the first term of the perturbation term. H naught is for an unperturbed term, and Hz is the perturbation due to the magnetic field. And then we can split this Hg prime in the 2 terms. There is the orbital angular momentum and the spin angular momentum, and Vx term, this one is the external magnetic field. And then these 2 terms we can define from this one E, this by, and this one is this angular momentum, spin, this orbital 1. And finally, you will get this operator for the perturbation theory. And so this perturbation depends on the number, on this term and ZHG. When the magnetic field is very small, it's this term also a smaller number, and this perturbation term also increase with the increase in the external magnetic field. So that's why first trying to derive the term energy, perturb energy in weak electric magnetic field. So this is the Hamiltonian energy, and we will get this energy if we want to this one, because we put N and L, it doesn't change with this magnetic field, and in presence of the weak magnetic field, total angular momentum J also doesn't changes. That's why this also changes the Ni change. It's only work on the Nj. And this total angular momentum, we can define L plus S equal to G, and then we need to figure out the S here. To find out the A, we can look on this figure. Actually, this spin momentum is the projection towards the total angular momentum. So we can say that the S, this one is a spin angular momentum, can by defining by this one. This is a unit vector of Z towards the Z directions, sorry, not Z, Z directions. So if we put the two both values in here, this term is coming from here, and finally we will get this one, and then this term is known as a lambda G factor. This term also defined and split a term, how many split term we will get this from this one. And then this, if this LG on the will act on these basis functions, and then we will get the mu b is EH over 2m. This is known as a Bohr magnetron. And now if we input all these terms in this work, we will get this energy. Part of energy is mu b Gj. This one is a lambda factor, and next term and Mj is coming from this J. So total energy would be there, and this one is, if we look on this one in the ground state, when n equal to 1, l equal to 0, and j equal to half, then we will get the two split term. Instead of 1 is plus minus mu b b x and 1. Plus is for when mj is a plus half and mj equal to negative half. And let's say once the strong magnetic field, strong magnetic field, and if we apply the strong magnetic field towards the z directions, only Lg and Sg work here. This dominate this term, so Ag is defined on basis on the Lg and Sg here. So it's very simple to explain. So to get a solution, so if we unperturbed energies are this one. From Lg and 2Sg, we will get the 2ml and 2ms1. But this one, it doesn't give the finite structure of this one. If we include this, as Aaron said, solve that one. If we want to include the relativistic effect and spin orbit coupling, then we will get finite structure from this solution. This one is for the relativistic term, and this one is spin orbit term. And we need to solve the FL here only, and we will get these two terms if we import this relativistic term 1 here and spin orbit SLG1 term here, because as I said, this one strong electric field only work on the z direction, so we will get Sg and Mg, and finally H bar M1 LS1. So if you beat all those terms, we will get final term here. This one is a part of a splitting energy term for the spin orbit, and this one. And so final splitting should be here, this one plus this one and plus this one would be the final energy of this. So thank you.
Okay, well, thanks. And if anyone wants to please him with questions, it is your chance. So I have a silly question. You are describing atoms in magnetic field and splitting of electronic levels. What happens if there is a spin associated with protons? How does it react to magnetic field? Are there any consequences?
But proton doesn't have orbital momentum, right? Spin momentum, so maybe it will include only the proton wouldn't interact with this one with external magnetic
Would
field.
proton interact with external magnetic field?
It should have, because it's probably, yeah, it should have.
Okay, good.
Because it's a spin momentum, angular momentum. So,
And NMR exists.
More chances to Jabed? No, not chances, questions. Chances to please hear these questions. If not, I thank Jabed once again. And now we are going from splitting of levels to another chapter where perturbation theory can be applied. It is, we all know from the common knowledge that atoms are held together if they have different charges or if they form covalent bond. But experimentally it is known that like cooled noble gases have some forces to hold them together, and even in other compounds there are some additional interactions that hold together electrically neutral species. So Brandon will provide solution to this puzzle with help of perturbation theory. Forde.
Perfect, thank you. All right, so we start off looking at the hydrogen molecule. We all know that for the hydrogen molecule, if the radius between the hydrogen atoms is on the order of the Bohr radius, they're going to be the nuclei are interacting, but also the electrons are going to be traveling between the individual hydrogen atoms and forming a single hydrogen molecule, right? Because that travel ultimately results in stabilization of the energy and delocalization of these electrons. But if you start to pull the hydrogen atoms a little bit apart, you're going to end up localizing the electron on each hydrogen nucleus. And so when you do so, then you can get this dipole, because no longer are the electrons delocalized across the entire system equally. You'd think of potentially an electron being in this portion of this hydrogen atom, and so as a result, it's going to have a partial negative charge in this region, and that partial negative charge can attract to a partial positive charge as a result of this electron being repelled from this region when it feels this electron and leaving behind partial positive charge, and so then these two can attract, and so we'll call that a dipole. So you probably remember this from Gen Chem when you were a freshman in college, or if you went to a non-American school, probably about 6th grade. So, okay. So, well, we always say, remember back to junior high. So, I never. Okay. So, if we imagine two hydrogen atoms, so their nuclei are going to be put at positions A and B, and so their electrons then are going to be at positions R sub A and R sub B. And so we can express the positions of these two nuclei by the vector between them. And so if we were to normalize that vector, we get n. And so for the purposes of this, we're going to assume that the distance between these two nuclei are much greater than the distance between the nucleus and the electron to keep it in the regime where the two atoms are distinct and don't form the molecular bond. And so we can express the electric dipoles by this expression, where Q is the charge, of course, and then just the vector between the nucleus and the electron. And so if we wanted to talk about the total interaction energy between these two atoms, we would use this expression. So here, so the W sub D refers to the dipole-dipole interactions, which are what we're going to be looking at today. I didn't tell the complete story in the previous slide, There's also quadruple dipole interactions and dipole quadruple interactions. You could think of those as in this region of space, there's a positive charge, right? But that positive charge is now going to attract an electron, partial positive charge. So there's going to be some tendency for electrons to go back into that region, even though there's that electron. So if you consider it across 4 electrons, it would form a quadruple, quadruple. But for this purposes, we're not going to be considering the quadruples. So we're only going to look at this dipole term. And so if we want to see the form of the dipole term, we're going to first think about the electrostatic potential at the region of the dipole. And so we're going to borrow some stuff from Aaron. So 1 over 4 pi epsilon, etc. Just pretty simple, straightforward. The dipole from A that's being felt at R is expressed by the electrostatic potential. And if you differentiate that, you can get the energy, or potential energy. So we put in our previous expression, which we had for d sub A, which was q times the vector between the electron and nucleus, and then we get something that looks like this. And so then the interaction energy from the dipole term can be given by this expression, where we've just simply taken the energy and dot across this d sub b in its explicit form as we wrote previously. And so now what we're going to set up our coordinate plane such that, our coordinate system I should say, such that the axis between this normal vector lies along the z-axis. And in doing so, oops, way ahead. In doing so, we now can express this whole thing as xa, xb plus yb minus 2 za, zb. And so then we're just going to make it an operator and write the same thing, only now where x's and y's and z's are the positions in the phase space as given by the operator. So the Hamiltonian of the system, the total energy, is going to be the isolated energy of each of the hydrogen atoms, plus this correction, which we're talking about, the interactions between the two atoms. And so for 1s atoms, we'll make them look like that, right? Where just n is 1, L and m is 0. And so the question then is, how do we evaluate the ground state energies, taking into account both this correction and its R dependence? And so if you think that the corrections that we're considering between dipole-dipole interactions versus the energy of the isolated systems is much, much smaller, then we're going to use perturbation theory. Let's consider it to be a small perturbation. All right, so the first order correction is, as written here, involves the form, looks like something like this. They make the argument that these the first order correction is going to be 0 for x's, y's, and z's, because the mean values of the components of the position operator are 0. So if we were to, when we defined our coordinate system by putting this vector along the z-axis, making this 0, 0, 0, we now have such that the average, if you average the x, y's, and z's of A and B, of A and B, you would get 0. But some we just have to consider the second order corrections. And so the second order corrections are given by this expression, as we looked at in class. And so if we were to look at this, we notice that when we put in our WDD, our dipole-dipole interactions, which we previously had, looks like this, but because it's squared, we'll get something over r cubed, or instead of r cubed, we'll get over r to the 6th. So we note that we have a proportionality for these terms of a constant over the radius to the 6th, which indeed is the dimensionality of the radius dependence of energy that we see in dipole-dipole interactions. Okay, so the last thing we can do is calculate the C, and so we can combine our previous results to get this expression. And so if we consider small n, or these two are small, n prime, we can get this expression, just pulling everything out front. And so if you expand, the cross terms are 0 due to symmetry. So expanding this part, the cross terms are are 0, but the direct terms go to something that looks like this. And so then if you combine what we have for that, multiply by 6, because there's going to be 6 direct terms, you would get 6 times e squared a to the 5th, and then just plug it in to our previous expression, and we can now quantify this correction to the dipole as a result of the interaction in the hydrogen atoms. And so it looks like this. So just notable, we now know the magnitude, approximately c, and we know the dimensionality, and it matches what we would expect, or what we previously learned in either Gen Chem or junior high about the dipole-dipole interactions.
Let's thank Brendan. And ask you questions. Jamie?
What is the difference of quadruple dipole attraction and dipole quadruple attraction in the second slide?
So we're talking about the existence of a dipole in one atom and a quadruple in the other atom, versus the existence of a quadruple in one atom and a dipole in the other atom. When we say dipole quadruple versus quadruple dipole. In this, we're just considering a dipole in a single dipole.
How do you get a quadruple in one of the others?
Okay, so if we're looking at the correction that we're considering due to this, what do you call squishiness of electrons. So we've only considered a single electron in the system, right? And so we said that this electron and this electron feel each other. We just consider 2 electrons feeling each other. And as a result, this one pushes this one away and leaves a negative charge or a positive charge, right? But now if you put more electrons into the system, because there's a partial positive charge here, other electrons are going to feel that and want to enter this region in space, right? Because now that we've formed a partial positive charge, we're going to have a tendency to reverse the interaction we just talked about, right? Or the field reverse. So now, if we put 4 electrons in, we'd have to also consider the interactions between these other electrons as far as their tendency to enter this slightly positive region of space. And so then that would be the quadruple, but we're not going to consider that. Does that kind of make sense? It's the best I can explain it, I guess.
So it's if you put more electrons in the system.
Yeah, if you're considering the interaction between more so I don't think it'd have to be distinct electrons. It could be these.
Okay, so you're ignoring the fact that the electron wants to go back into that positive region of space that it left behind.
Right, it maybe that'd be this electron or other electrons in the system.
So you have the negative electron, the positive region of space, the hydrogen, positive charge. Where is the rest of the negative charge? The other electron?
So this negative charge here.
Well, I'm looking for 4 charges. I'm looking for, that's
Okay,
the
so
right?
Yeah, so now if you consider, say, this electron, or an electron wants to be on this side, because this side of the atom is partially positively charged, and this side is partially negatively charged. Now you're going to go back to considering this one maybe slightly less, a slightly smaller negative than this positive, right? Because this isn't a full positive. But electrons are going to want to be, so figure, say, a smaller delta minus, because electrons want to come here. And as a result of that smaller delta minus, electrons are going to want to leave here. So a smaller delta plus. So then you'd have 4 partial charges, not charges, but 4
So you're talking about continuous distribution of charge density.
Sure, yeah.
That can take shapes and match the. Provoking question. I don't have answer to.
Uh-oh. Then I'm not going to have an answer to that.
Well, you are the expert in Van-der-Waals from now on.
Yeah.
So if one of these hydrogen atoms is excited, is not in the ground state, will the Van-der-Waals interaction will be stronger or weaker?
Oh boy.
Just intuitively or based on what you've.
So.
Or how to start thinking about it.
The paper actually derived it further on, but I don't remember if it was stronger or weaker, but I would think it would be probably weaker because it's more localized orbitals now. It's not in the s orbital.
But if you go to excited, it can be more extended in space?
Oh, yes. So maybe stronger?
Intuitively, I would think so, but I don't know.
Ah.
You are investigating it deeper.
Which one is more localized, ground state or excited?
The ground state.
Is more localized.
Well, yeah. Yeah.
Anyone else wants to support discussion with Brandon? If not, thank him once again. And we have last presentation of today that establishes a bridge between chapter that we just are completing and the next chapter that we are going to start. So the presentation by Sam Brown will be dealing with experimental technique of the scanning tunneling microscopy, and we are departing from time-independent perturbation theory that introduces changes in energy levels and changes quantum states, and starting navigating towards time-dependent perturbation theory, where occupations are changing and there is some dynamical processes, some non-equilibrium processes. So the application that Sam is going to mention is in transit. Floor is yours.
Thanks, Dimitri. So as the experimentalist in the group, I figured I'd talk about something experimental, like scanning tunneling microscopy. It was developed by Gerd Binning and Henrik Rohrer at IBM in 1981, and 5 years later won the Nobel Prize in Physics, so that's always good. Here's kind of just some of the basics. We use STM, or people use it, I haven't used it personally, to take images of surfaces as well as get local density of states. So you have a metal tip, and then the substrate that you're going to be looking at, and there's going to be vacuum in between, and the electrons can tunnel through that vacuum into the substrate or from the substrate into the tip, which creates a current. And based on the amount of current that is generated, we are able to generate a picture. So here's a single-walled carbon nanotube, and then graphite. Some of the different things that will change the amount of current is the tip position, the applied voltage, and then the local density of states of the sample. So I have quite a bit considerably less math than you guys all did, but here's a little bit of what it is. We can try to be able to derive the current based on the local density of states, starting with Fermi's golden rule. So Fermi's golden rule is where we use perturbation theory, so I don't have much on how that was used to derive that, but starting with that, we are able to then be able to get the current based on the local density of states for the tip and for the substrate, where this M factor is the tunneling matrix. So it's kind of like a probability for the electron to tunnel through this tip to the substrate. So some more exciting things, I guess. So if you have this is like a band structure diagram for these. When applying a voltage, you're able to get images of the occupied states as well as the unoccupied states, depending on the voltage that you apply. So in this case, by having a negative voltage, the Fermi level, negative voltage to the sample, the Fermi level of the sample is increased, and then we're able to have electrons travel from this state to the tip. So now we're looking at the occupied states, but by doing a positive bias, we're able to get the opposite of that. So then the electrons are flowing from the from the tip into the sample into those unoccupied states. Here's just a cool application of it. This is a silicon nanocrystal where they did STM all the way across, and we're able to calculate the local density of states based on the current, and use that to kind of determine whether there is different defects and such within it and the effects on the density of states.
Okay, well, thanks, Sam. And I anticipate there will be some questions.
Can you go to the first slide with the graphite picture? Why can't you see the hexagonal rings? Is it because it's seeing the atom below? Graphite. Yeah,
So I think this is several layers of graphene.
Yeah.
Yes.
Yeah, but is it seeing the atom in the middle of the layer below? Because it's the hexagonal shape is there, but there is an atom in the middle. Is that the atom from underneath?
That would be my guess.
Because
It's not
it
single
doesn't
layer.
look like graph. Because graphite,
Graphene is single layer. Graphite is.
right? Graphene, but graphite should look like graphene if the lower layer doesn't show up, right?
Yeah, right. But that'd be my guess, is that you're seeing the one below it.
Would you like to challenge him back with a question about resolution? Okay, on behalf of Sam, I'm challenging you back with the question.
Okay.
How does this picture of one atom thick tip approaching the surface and detecting individual atomic resolution, how does it go along with uncertainty principle? Would you think it is possible to get single atom resolution, or there are some fundamental difficulties?
It looks like it's possible.
No, but if you do not look on the figure.
It should be possible.
Can you derive?
No, you always have some uncertainty, and with going to that small of system, your uncertainty dramatically increases. So what you're trying to do is you're trying to make it frozen, but if you make it frozen, then everything else kind of goes to craziness. So I think it's if you have more certainty, then you get less in another, right?
So energy, time, or uncertainty? Is it energy, time, or uncertainty?
Oh yeah, certainty.
Are you talking about minimizing the uncertainty so that
No,
it's h bar over?
The minimum you can do is h over 2.
Yes.
If your operators don't commute. And I don't think position and total energy commute, right?
There is no position energy uncertainty principle. There is position momentum and energy time.
Yeah, position, moment, energy.
And here what you're detecting is voltage.
Which is
But you're looking. Well, we should let speaker to speak.
No, you
But
guys are doing great.
there is an hybridization of quantum states of orbitals belonging to the surface and to the tip.
Yes.
And both are extended in space.
So you're looking at the. So you're looking at the position momentum uncertainty principle. Well, the position is.
So we can fix position of a tip, but we cannot fix position of an electron.
You can fix the. You can fix the position of the tip.
But both orbitals on a tip and on a substrate are extended systems.
Okay.
Like distributions.
Okay. But the layer below should be fainter. Still?
Not only the layer below, also the neighbors. It hybridizes not only with the one below, but only with
Oh
the
yeah, but it
neighbors.
scans. That's why it scans. It scans. So the neighbors the neighbors should be the same resolution, but the layer below should be fainter. It's like the nanotube. The layers that are so it's scanned at a certain height, and the top of the nanotube that's close to it is really bright. But as you go to the edges, you don't see it anymore.
Well, we do not know what is shown in this image, and does it mean that brighter corresponds to stronger signal, or it is weaker signal?
No, it's stronger.
Huh?
It's
How do you
stronger.
know? How do you know it?
Because you can see, like, there is no nanotube over there where it's red, where it's dark red. There is no nanotube. There is no signal.
Okay. Brandon?
Is this is this what am I trying to say? Oh, is this averaged over a lot of bunches over many different scans?
Like I said, I haven't actually used this.
No.
I guess it would be just one scan. Probably you'd have too much size resolution to get several.
Why would you need 10 scans?
Because it's how do they move the table so precisely over a single scheme?
No, the table stays fixed and keeps.
Yeah, the tip's vibrant, right?
Well, it
So
goes back and forth.
You just jump nearby and the whole image is ruined.
Yeah, you can't.
Store your questions and be prepared. In a couple of weeks, there will be a seminar speaker on this subject.
I took graphite pictures with just a very small STM in lab, and then it was like a little orange one.
STM.
STM, yeah. It's like a little orange. Have you seen it? It's like very popular. It's like a lot of schools have it. It comes in a box. It's this big. That's all the equipment you need.
Huh.
And it comes with a graphite piece, and you peel with a tape. Use tape to peel it, and
Take a
then you put
graphene or
to peel the graphite. And you stick the freshly peeled surface, and it scans, and it comes out. And
did you see the hexagonal layers when you did it?
yeah, it's really visible. And the one in the middle of every hexagon is faint because it belongs to the layer below.
Interesting.
That was kind of the point of the lab that we did. So
Yeah. It's interesting, right?
maybe this is like some kind of higher voltage.
Is it here at NDSU?
No, it's an MSU.
Okay. But they have this equipment.
Yeah,
And you can purchase
maybe NDSU has it too. You can purchase it. Yeah, and it's not very expensive. It's
Okay.
And this you has a TEM.
NDSU has a professional STM. Like it's a big
No,
machine.
they have a TM. No, I don't know of an STM.
UNT has STU.
Sensi has STM. Sensi.
I thought
They have
something
a
with
SE.
that kit.
It used back when I worked there. It used
Can we go one slide forward? Here. So, what is perturbation here?
The perturbation was done within the development of the golden rule, from what I found.
So, what is H prime?
That was the
Either
perturbation.
M,
Oh, yeah, that was.
but where H prime comes from?
Um, what was the perturbation?
Yeah, what is H prime? What is the nature? How to write it explicitly? Probably your psi and chi are orbitals of the tip and substrate.
Oh,
But
yeah.
what is H prime?
The position.
Hmm?
Is it position?
Or
it's Hamiltonian, some Coulomb, or that local electric field.
or one can
An electric could be an electric field. Because that's what.
okay. So it's a dipole interaction, but then it will affect all the energies. Can one remove the H prime and just use the overlap? Just based on the figure for tunneling, there is vacuum in between, there is nothing.
Yeah.
So probably H prime can be just free space Hamiltonian, remove it. Okay, so is there any connection between Fermi-Golden's rule, Fermi's golden rule, and perturbation theory? Are they connected?
The derivation of Wikipedia gave me use perturbation theory to get Fermi's golden rule.
So they are connected?
Yep.
Good, yes.
But it's time dependent.
It's correct. But we are using this presentation as a bridge to next chapter.
So what is H prime? Question to you.
Huh?
What is H prime?
Let's discuss it when we meet next time. More questions to Sam? Everyone is happy? Let's thank him once again. So, thank you much for contributing your enthusiastic presentations and presenting and supporting discussion. Everyone gets A on the midterm. So if you do not fail, you are on the right path to perfect completion of the course. And with this, let me announce completion of the meeting number 11. We are going off record, and I'm staying here a couple of minutes just in case you have more questions.